Assalamu alaikum, my dear students. Welcome to the course Solid State Physics 1 with the code PHY302. Now this is the second part of the course Mathematical Physics. In the first semester you might have studied chapters starting from vector analysis up to the complex variables. All these topics which you studied in first semester are very helpful in solving various problems on physics. You must note that the main objective of this course, Mathematical Physics, is to get trained in solving differential equations and other topics because differential equations are so important in physics, as you will see during the course of this study. Let me first tell you about the books which we will follow in studying this course. Our main textbook is Mathematical Physics for Methods of Mathematical Physics for Physicists, written by George Orfkan. Now this book has various editions available in our library, but I have selected this edition, which is the 7th edition, and I will provide you the soft copy of this book, but occasionally we will be consulting other editions of this book, which I will mention when I will be using this. But for the time being, you must possess the soft copy of this, which I will load on the group. Now this is the chapter on differential equations, which we will start, and this is in fact the chapter number 8 from this book by Orfkan, and okay, this is the start of this chapter, differential equations. Now here in article 8.1 you will see the importance of differential equations in the physical problems, and in fact the differential equations which we encounter whenever we study any topic of physics, we end up with a partial differential equation. For example, equation number 1, which is the Laplace's equation, and this equation is del square psi is equal to 0. Now this is very common and very important equation which occurs in the studies of electromagnetic phenomena, including electrostatics, dielectrics, steady currents and magnetostatics. B. This equation is also seen in hydrodynamics, irrotational flow of perfect fluid and surface waves. It is also common equation in heat flow in problems with gravitation. The next important equation, rather the most important equation written in the generalized form, is del square psi is equal to minus rho over epsilon naught. and this is the Poisson's equation, which in fact covers the entire electromagnetism. It is also known as the wave equation, Helmholtz equation, and so you must go through this list carefully. We have this equation seen in elastic waves in solids, including vibrating strings, bars, membranes, and we have this equation in sound or acoustics, electromagnetic waves, nuclear reactors, and so on. So we have other topics of physics in which this equation is seen. So I would suggest that you should go through this list, and you will then realize what is the importance of partial differential equations in physics. And in this chapter we will learn how to solve partial differential equations, because to complete any topic on physics, when we encounter with a differential equation, we will have to solve this equation to complete this topic. So the solution of partial differential equations, particularly of second order, is a very important topic which we must study. Okay, so this is in fact page number page number 438, which completes this list I have just mentioned, and then we will jump over to page number because, as I told you, it is the partial differential equations which are very common. So in order to solve a partial differential equation, we have to convert this differential equation, partial differential equation, into an ordinary equation, in fact a set of ordinary equation. And you must recall that the operator del square is a partial differential operator. Okay, so in order to convert a partial differential equation into an ordinary differential equation, the technique we use is the separation of variables. And I will also advise you to get my handwritten notes from the photocopier shop outside the department, who has my notes. So you must get my notes on chapter 8, that is the differential equation, because this handwritten notes will give you the detail of so many jumps which you will see in this book. So, and we will occasionally consult with the notes as well. Okay, so this is equation number 8.19, is the most general form of a partial differential equation in physics. This equation with various values of k covers all the topics of physics. Okay, this is known as the Helmholtz equation, and we have to separate this equation into a set of ordinary differential equation. So mind you, this operator del is a three-dimensional operator. In Cartesian coordinates it has the value second partial derivative with respect to x square plus second partial differential equation with respect to y and partial differential equation with respect to z. So this is so when we use the technique of separation of variables, the detail of which you will see from my notes which I have just mentioned, you will end up with this equation when it is converted into a partial differential equation. This function psi is, which is a function, implicit function of x, y, z or theta phi in spherical coordinates, or rho phi z in cylindrical coordinates. So when we have to separate, so we will substitute psi equal to, say, capital X as a function of small x only, plus capital Y as a function of small y, and capital Z as a function of small z. Or if you are using the spherical coordinates, then this function will be converted, it will be written as equal to capital R as a function of small r, plus capital theta as a function of small theta, plus capital phi as a function of small phi. So instead of psi, our ordinary differential equation will show up capital R, capital phi, capital theta. So the phi part of this equation, as you will see from my notes, is this equation d2 phi over d phi square, this is capital phi, derivative of capital, second derivative of capital phi with respect to the spherical coordinate phi, is equal to minus m square phi phi. And similarly, if you are dealing with Cartesian coordinates, it will show up like this. And the theta part of the equation is written here as the equation 8.23, and the previous equation was the phi part, and then the radial part of this equation is also will be seen here. So okay, so in this section we have converted our partial differential equation into a set of three ordinary differential equations, whether you are using Cartesian coordinates or polar coordinates or the cylindrical coordinates. So this is, you must go through this page and particularly my handwritten notes to understand what I am saying here. Okay, so after this step that you have converted the partial differential equation into a set of ordinary differential equation, now moving towards the solution, we have to consider an important topic, which is the singular points. Singular points are the points of a differential equation and here is the description of singular points. This is the most general form of a differential equation of second order, equation 8.31. We have the second derivative of y, then we have a polynomial px multiplied with the first derivative, then we have the polynomial q multiplied by the function y. So equation 8.31 is the general form of a second order differential equation, and this is the equation we will going to solve. We will learn a technique to solve this equation. So here, as we are discussing the singular points, so the function y, which is in fact the function of a physical concept, so this function will have a point of expansion. The technique we will solve here we will discuss here to solve the differential equation is the Frobenius series method. So we will use the series, infinite series of the function y, and that's why we have a point of expansion. So this point of expansion is either a regular point or a singular point. So here we have described that if either px or qx diverges as x tends to x naught, but x minus x naught into px and x minus x naught square into qx remain finite as x tends to x naught, then x is equal to x naught is called a regular or non-essential singular point. So here x naught is the point of expansion. X is our variable, so it depends on whether the polynomial capital P and the polynomial capital Q, if they do not tend to infinity, that is if they are finite, both of them, then our point of expansion is an ordinary point. But if either capital P or capital Q becomes infinity as x tends to x naught, then this becomes a singular point. And the singular point, there are two types of singular points. If px tends to infinity or qx tends to infinity as x tends to x naught, but if you multiply px with x minus x naught and if you multiply qx and with x minus x naught square and they become finite, then the point of expansion x is equal to x naught is called a regular or non-essential singular point. But if by doing so, that by multiplying p and q with the factors x minus x naught and x minus x naught square, if they still remain infinite, then the point x is equal to x naught will be an essential singularity, as described in point 2 here. If px diverges faster than this, so that x minus x naught square into px goes to infinity as x tends to x naught, or qx diverges faster than 1 over x minus x naught square, so that x minus x naught whole square qx goes to infinity as x tends to x naught, then point x is equal to x naught is labeled as irregular or essential singularity. Normally our differential equation carry the point of expansion as x naught equal to 0 or x naught is equal to infinity. or it can be some finite constant. So but if we have to look whether our point x naught, which is now infinity, then we have to put y is equal to 1 over z in our differential equation, so that if we have to look the behavior of the point x naught tending to infinity, and when we put x is equal to 1 over z, so it will become to check whether z tends to 0. Whatever behavior of the differential equation shows with z tending to 0 will be the same as the behavior of the differential equation in terms of x tending to infinity. So in these few steps, the discussion of the singular point x naught equal to infinity is discussed, how to check it, and you will also see the detail of this from my notes. Okay, so after discussing the role of the singular point or the regular point, now let us move. Here is an example which shows that x square y double dash plus xy dash plus x square minus n square into y is equal to 0. This is a famous equation known as the Legendre differential equation. Now if we find the value of px, if you compare this equation with the standard form discussed previously, in which we have had the standard form as y double dash plus px into y dash plus qx into y. So we have to divide this equation by x square to convert this into a standard form. So when we divide this equation by x square, we have here 1 over x, here y double dash, and here x square minus n square over x square, so that px becomes 1 over x and qx becomes 1 minus n square over x square. And if you have to discuss the role of x tending to infinity, then as I told you, we will substitute x is equal to 1 over z, and then the px becomes equal, pz becomes equal to this, and qz becomes equal to this, and we have to see the role of the point z is equal to 0 in our differential equation, and then recognize what type of point we have. Now this is the a set of equations. Well, you have to solve these problems 8.4.1, exercise 8.4.2, which I have done in my notes, and this table shown here carries 8 equations, and these 8 equations cover the entire physics. We have the hypergeometric equation in the standard form, Legendre differential equation, Chebyshev differential equation, confluent hypergeometric equation, Bessel's equation, Laguerre equation, simple harmonic oscillator, and Hermite equation. So all these equations are partial or differential equations, and you know that and here in this table the regular singular points and irregular singular points have been detected, and you must just look at this table, and we will consult this as a reference. You don't need to remember this table, but just to have a close look. In this set, the most general equation is the Bessel's equation, this one, so you must recognize this equation, and then the next important equation is the Legendre equation, and then we will go to the Laguerre equation, Hermite equation, and this is the simple harmonic oscillator. Okay, so I would recommend that you must go through exercises 8.4.1 and 8.4.2. okay, so this is the now we will solve these equations, the standard equation 8.36 written in the standard form. So we will attack this equation and find its solution, a solution which is always available by this technique known as the series solution or Frobenius series method. Right. So what we will do in this technique, why we call it the series solution, because in here we will assume that our function y can be written as a series. So this is the series, infinite series, which we will use instead of yx as equal to sigma lambda is equal to 0 to infinity a lambda x power k plus lambda a naught not equal to 0. So when we say that we have to solve the differential equation, it means we will find the value of y, and this value has been assumed as an infinite series. Now this infinite series as a powers of x carries an infinite number of coefficients a lambdas. So we have to find these coefficients a lambdas by this method, and once these coefficients are known, then it means this series is known, which means that this equation has been solved because yx has now been determined. And so if we write y as equal to this, then the first derivative of y is equal to this, the second derivative of y is equal to this, and we will simply substitute the values of y dash the first derivative, y double dash the second derivative into our differential equation. Now as a prototype, we will discuss this technique using this famous equation, which is in fact the equation of a harmonic oscillator. Y double dash is equal to omega square y is equal to 0, where omega is the frequency of the harmonic oscillator. So we will elaborate this technique by solving this equation using the Frobenius series method. So as I told you, we have to substitute the value of y dash and y double dash into our differential equation, and when we do this, we end up with this equation 8.42. So this is the second derivative into x square, and this is the first derivative into x, and equation 8.42 is the result of substituting the series of y in our differential equation. And then we will compare the coefficients of the same powers of x. So as a first step, we will compare the coefficients of the minimum power of x. Okay, so if you look at the first term, the minimum power of x with lambda is equal to 0 comes out to be k minus 2. So we will have the equation a naught into k minus 1 because we have substituted lambda equal to 0 into x power k minus 2. So this is the first term, and in the second term, if we try to find out the minimum power, So here the minimum power with lambda is equal to 0 is x power lambda. In this first term, the minimum power was x power k minus 2. Here the minimum power is xk. So it means the minimum power, which is x to the power k minus 2, only appears in the first term, and in the second term there is no term with x power k minus 2. So the coefficient of the minimum power of x is a naught k into k minus 1, and here the coefficient is with minimum power of x as x power k minus 2 is not present here, so we will take the coefficient 0 from the contribution of the second term. So we will have this equation a naught k into k minus 1, which was the coefficient of the minimum power x to the power k minus 2 from the first term. The second term does not have the coefficient with x power k minus 2, so the second term coefficient is 0, and the right hand side of this equation, which is 0, is written here. So we have this equation a naught k into k minus 1 equal to 0, and this equation has been obtained by comparing the coefficient of the minimum power of x, and from this equation, because a naught cannot be 0, so we end up with the result that k into k minus 1 is equal to 0. Okay, so this equation 8.43, which has been obtained by comparing the coefficients of the minimum power of x, this equation is known as the indicial equation. So the indicial equation of a differential equation is always obtained by comparing the coefficients of the minimum power of x, and this equation will give us two values of k, as we see here. The first value is k is equal to 0, and the second value is k is equal to 1, and these two values of k will furnish the two solutions of our differential equation, because our differential equation is a second order differential equation, so there must be two solutions of this equation. So the first equation solution will be obtained by using k is equal to 0 in the series method, and the second equation will be obtained by putting k is equal to 1 in the series method. Okay, so before considering these two possibilities for k, we return to equation 8.42 and demand that the remaining net coefficient, say the coefficient of x to the power k plus j, in fact what he is talking about here, the next step is that we will now compare the coefficients of the general power of x. In obtaining the indicial equation, we compared the coefficients of the minimum power of x, but now we will compare the coefficients of the general power of x. So if you look at your equation, this one, and you substitute the general power, so you will take lambda is equal to j, and when you put lambda is equal to j and substitute these values of y, y dash and y double dash in your equation, you will end up with this equation, the comparison of the general power of x from the first term, from the second term, and the right hand side is 0. It is aj plus 2, k plus j plus 2, k plus j plus 1 plus omega square aj is equal to 0. And this equation will give us aj plus 2 is equal to this. So, as I told you before, if you have any confusion of deriving this equation, you must go through the details given in my notes, so which you can get from the photocopy shop outside the department. So this is a two terms recurrence relation. So this equation will give us the values of all the coefficients A0, A1, A2, A3 of our series expansion, and as I told you, if you find the coefficients, it means the solution is known. So for example, if Aj is given, say A0 is given with j is equal to 0, then you can find the coefficient A2 from this expression by writing j is equal to 0. So this will give you from the value from the coefficient A0 the coefficient A2, and once A2 is known, you substitute j is equal to 2 and you get the coefficient A4, and similarly by substituting the coefficient A4 in this equation, you will jump to the coefficient A6 and so on. So you will, starting from the coefficient A0, you will go to A2, A4, A6, A8, etc. up to infinity. However, the other coefficients A1, A3, A4, which are the odd coefficients, are missing here. But by using equation 8.44, you have determined the coefficients A2, A4, A6, and so you have half of the coefficients. But mind you that the infinite series, if it is made half, it still remains infinite. So whatever solution we will get from here will give you the solution of the differential equation. Okay, so you must go through the description given here, and this is now equation 8.45 has been written by taking k is equal to 0 of the initial equation. As I told you, said that when you put k is equal to 0, you will get the first solution. So these are the coefficients with k is equal to 0, and they give us the coefficients of the first solution. And when you put k is equal to it was k is equal to 1, you will get the coefficients of the second solution. So here are the coefficients of the first solution, A2 as A0 omega square 1 into 2, because we will substitute j is equal to 1 and so on. So these are the coefficients A2, A4, A6 and so on, the coefficients of the first solution of the differential equation. Similarly, when you put k is equal to 1, you will end up with the coefficients here, the recurrence relation here 8.48, which will furnish the coefficients A2, A4, A6 and so on, and which you can generally write like this. So now we have obtained the relevant coefficients, and we will simply substitute these values of these coefficients with k is equal to 0 and here with k is equal to 1 to get our first solution, which is A0 over omega into sine omega x, and the second solution, the first solution, which was obtained earlier by taking that was A0 cos omega x. And so we have obtained the solution using the series, Frobenius series method of the differential equation representing the harmonic oscillator, and you already know that this harmonic oscillator equation has the solution as sine omega x and cos omega x. So we have obtained the same solution, which shows the authenticity of this technique, which is the Frobenius series technique. Okay, so let me finish here, stop here, So in this lecture we have just introduced the Frobenius series method, and we have applied this technique, we have elaborated this technique on solving the differential equation of the harmonic oscillator. But you can use the various steps of this technique, that is using the series, finding the indicial equation, finding the recurrence relation on any given differential equation of second order, and you will find the solution. In most of the cases, say 95% cases, you will succeed with this solution. So in our next lecture we will apply this technique, we will elaborate this technique on the most general equation which appears in problems of physics, which is the Bessel's differential equation. So we will solve the Bessel's differential equation using this technique, and we will discuss the physics and mathematical aspects of this. Okay, so let me remind you again that you must get my handwritten notes from the bookshop, or any one of you can get the original copy from myself from the department, and get the photocopy, master photocopy, and the rest of you can get the photocopy of these notes of this chapter. It is very important that you must possess these notes along with you, apart from this book which I have loaded on the group, and these two references you must possess whenever you attend my lecture. Okay, thank you very much.